In our last video, we explained the trick to understanding the Black Scholes model, that it is a reinsurance premium analog, and we even worked the inputs of the formula. Now, if you watched that video, that's when we encountered two very strange things. The first was that the volatility doesn't appear anywhere in the written formula, although it is required as an input to the worksheet solution. And while we're at it, what does volatility mean exactly? And then second is that the written formula requires inputs called D1 and D2, but they're not required inputs to the worksheet solution, meaning you don't even type inputs for D1 and D2. So today we will explain the mysteries around this model and then some. Just a warning, this will require a fair deal of algebra, which we revisit as a walkthrough rather than as a way to prove the model per se. There are key insights that are useful to point out to get the key intuition for practical computational purposes. And that will be the purpose of the walkthrough, to surface and point out these key insights. At the end of this video, you should be able to understand exactly what's going on when computing the option price using Black Scholes and understand the intuition behind it as well. There are actually two kinds of options, European options and American options. And this is not a reference to where they're issued, but when they can be exercised. For European options, this can only be exercised at maturity, while American options can be exercised anytime. So it has nothing to do with where they are issued, that's just the convention. Now, the Black Scholes option pricing model is used only for European options. American options are priced differently via binomial models. Now, as we stated in our previous episode, and please watch that, the Black Scholes model gives the option price that can be thought of as the present value of the mathematical expectations of all the differentials above the exercise price K, at least just for the call option. That is, under certain given assumptions, it produces this written equation, the famous Black Scholes option pricing model. Now, let's revisit the technical details as we promised last time. First, we need to discuss the probability distribution function of a normal distribution versus that of a log normal distribution. This is because the Black Scholes model assumes log normality. That is, it's not the random variable x that is normally distributed, but ln of x is. Meaning after applying a log normal transformation, the transformed variables are normal. We need to show the log normal distribution because it features prominently in the whole equation of value. So this is what a normal distribution looks like. This is what a log normal distribution looks like, at least for the probability density functions. Now, assuming log normality, we can now attach a probability distribution function to g of x as follows to get the reinsurance premium analog. And we did this last time. So what's going to be new is that we're now going to attach the log normal PDF into this formula, where we replace g of x with the probability distribution function for log normal distributions. Next, we get the present value of this reinsurance premium using the risk-free rate of return. And now we have the price of the call option. And for our purposes, because it really looks horrible, we'll just call it the horribly complicated log normal call price. It's equal to the present value of this reinsurance premium analog. Here it is assumed that the stock moves forward in time via some log normal distribution, which we represent as some accumulation function a of n, meaning a of n is equal to 1 plus r1 times 1 plus r2 times 1 plus r3 and so on and so forth. Notice that if we get the ln of a of n, it produces a linear combination of different ln 1 plus r. It is this ln transformed numbers which is normally distributed, which is why x is log normal. So this is what it looks like. Here we get the average of the ln's and the standard deviation of the ln's to get the average and standard deviation. And this leads us to the first insight. The mean and standard deviation of the ln1 plus r's is the key point here, not the mean and standard deviation of the r themselves as we used to do working on Markowitz portfolios. So let's move on. Next, we get the mathematical expectation of this accumulation, and we multiply it to the price of the stock S to get the future price S sub n, and S sub n is therefore S times the expectation of the accumulation function A of n. And this leads us to this formula. After accumulating S to S sub n, we now get the present value of that future stock price S sub n. However, when we get the present value of the future price, we simply use the risk-free rate using an assumption of a risk-neutral world. This is just a fancy way of saying, hey, let's all pretend we can use whatever rate we can, and let's use the risk-free rate of return for now because, the world is risk-neutral. Yeah, I know. Wouldn't it be cool if we can argue like that always in university? But anyway, bear with me on this. We can justify it later in some future video with the brilliant argument Black and Scholes used. But for now, let's just run with the risk-neutral world argument. So we have this almost circular-looking argument, which gives us the equation. The current price of S is actually the future price accumulated by A of n, and then we get the present value using the risk-free rate of return. Now, the S will cancel in both sides, and this implies that 1 is equal to e raised to this exponent. Now, for the right-hand side to be equal to 1, the exponent must sum to 0 to get e raised to the power 0 to be equal to 1. This implies that negative r times n plus n times open and close parenthesis mu plus 0.5 variance should be equal to 0, which implies that mu should be equal to r minus 1/2 variance. And here we get to the second insight. The mean of the transform variables does not matter. Only the risk-free rate and the standard deviation of the transform variables do. And here we remember that we are working with the standard deviation of the ln1 plus r's. We're still keeping that in mind. Now, substituting mu into our previous horribly complicated log-normal call price, we now have something looking even more horrible, but have patience. They still conform to a log-normal distribution, which is why they look very overly complicated. But the intuition remains, and despite being complicated, it's still saying it's the ln of x, which is normal, not x. So we have this call price, and now mu disappears from the equation. Now, we break apart x minus k by distributing all those horrible squiggly notations to x and to k. So we have this breakdown into two terms, which already starts to look like what we see in the Black Scholes model. Next, we manipulate the expressions to get formulaic cumulative normal distributions. That is, we try to transform those horrible squiggly notations into something familiar as log normal. But since it's too complicated to recognize anything by the sheer clutter of it, let's simplify and transform all x's into y's and see if we can recognize anything when we look at it as y's. So let y be equal to this equation, and notice that it's nothing but the power of the exponent. And writing it like this, the exponent can simply be written as e raised to negative 1/2 y squared. Much easier to read, and the clutter is cleaned up. Then we need to get the first derivative so that we can transform the equation in x to an equation in y. Also, we need to solve for x to replace the variable x. Remember, we're using x minus k, and we're transforming everything into a y, so we need to replace that x in the x minus k into something expressed in y. You can pause here and even try to do the clever math if you like, but the point here is to remove all x's and replace them in y terms. Thus, this algebra discussion. So, given our y, we can show that x is equal to s times e raised to the power this complicated squiggly notations. Now, finally, almost everything is transformed from x to y, except the exercise price k as the starting point of the integration in terms of y. This means we need to transform k into something consistent in y terms. And we do that by computing for what we call f, which is now the starting point integration in y, analogous to what k was for the variable x. So we set f is equal to this ln of k over s minus n times the open and close parenthesis r minus 1/2 variance all over standard deviation times square root of n. We now have a very simple exponent for e raised to the power 1/2 y squared, and the only problematic part is the first term. So let's try to simplify the first term. To reduce the clutter, we'll just work on the exponent part again. Please feel free to pause if you want to work out the algebra yourself. But the point here is not the algebra, but it's really to express the exponent into something resembling a normal distribution. And by some clever tricks, we can transform this into a y minus something quantity squared, and therefore we can express that first term into the simpler term as follows. And the second term will simply be like this, and therefore we now have the transform equation in y that is simpler to interpret, and which looks like this one. And I'm not even going to read this anymore. The first integral is the area to the right of f minus sigma squared of n. The second integral, the area to the right of f. And this is f, remember. However, by convention, especially when we're going to use Excel, we need the area to the left of z so that we can use the Excel function norm as this, which is the standard normal distribution curve. So we get the area to the left of negative f plus sigma squared root of n instead, and the area to the left of negative f. So doing negative f, we're going to get this one. And since negative ln of ks is equal to negative ln of k minus ln of s, and then therefore it's going to switch the sign, and it's going to be equal to ln of s minus ln of k, and therefore it's going to be equal to ln of s over k. And it essentially flips the numerator with the denominator, and therefore we'll have this new negative f's and negative f plus sigma times square root of n as follows. And this is exactly the inputs to the Black Scholes model, where d1 is equal to negative f plus sigma square root of n, and d2 is just negative f. Now, here's the third insight. The standard deviation of the ln 1 plus r's, the risk-free rate, and the time to maturity along with s and k determine the whole inputs d1 and d2. d1 and d2 themselves are inputs to the standard normal cumulative distribution corresponding to all prices of the original stock price x above k, assuming a log normal distribution. So that's what d1 and d2 are saying. And then fourth insight, only the volatility sigma is constructed and not observed anywhere. Everything else are observable inputs to the Black Scholes model. There's significant leeway of thinking what could be considered sigma. In our example, we will use the standard deviation of the ln1 plus r's as the sigma. And assuming that the ln1 plus r's are independently distributed, this means that if we have a daily variance, the annual variance, which is what is needed in the formula, can be thought of as follows. The annual variance is equal to 365 times the daily variance. And this reduces to the usual daily standard deviation times square root of time when we get just the sigma. However, number of actual days can also be used as well rather than 365. Others, they completely skip this and just use the option prices already visible in the market, then try to work back the sigma or volatility implied by the market pricing, meaning they use iterative methods to compute for the sigma and use that as the sigma for the stock. In this case, this is implied volatility rather than a computed volatility based on the ln1 plus r's that we're using over here. Now, we're going to apply this to computations. We are providing the worksheet to compute for the Black Scholes call option, where we demonstrate the key insights we discussed above and use it for computational purposes. We start with dummy data of prices, then we get the ln1 plus r's, then we compute the standard deviation, and then we're going to see how we're going to use the d's and see how we're going to compute the resulting call option price. Okay, that's all for today. I hope that was worth your while. Next up would be put-call parity, option sensitivities, and some mnemonic devices to remember the option sensitivities for puts and calls. Alright, so kindly like and subscribe to help support the channel, and see you next time!